Okay, let's continue. There are two ways of ionization. First one is electron ionization. That means using electrons to ionize molecules. Okay, so electrons are emitted from a hot filament and accelerated through usually 70 volts before interacting with incoming molecules. Okay, so this is the molecule. Now it enters uh, the spectrometer, okay, mass spectrometer, and then electrons are produced from hot filament, okay, and then the molecules and electrons are collide, okay. But now electrons are accelerated by 70 volt potential difference. So electrons gain energy by 70 electron volts. Okay, and then this amount of energy is enough to ionize these molecules. Okay, now molecules usually lose one electron. Okay, and then it becomes a positively charged ion, yeah? And then usually radical. Okay, and then electrons this electron now lose energy because it now collide with this molecule. Okay, and and also this one the one electron is ejected, okay, from this molecule. Okay, so there are two electrons of different energies. Okay, so electron kinetic energy of 70 electron volt is much greater than ionization energy of molecules. So usually this is molecular ion, okay? But usually fragmentation occurs, okay? Yeah. Let's consider this formaldehyde, okay? And the formaldehyde, let me see, this is sigma bond. Ionization energy is only 15.9 electron volts, okay, and this one pi bonding electron, this ionization energy is only 14.1 electron volts, and this formaldehyde has non-bonding electron, and this ionization energy is 11.0 electron volt. Okay, so when this formaldehyde molecule collides with the 70 electron volts, this high energy electrons, usually these chemical bonds are broken, so fragmentation occurs. Okay, so this list shows the post ionization energies. Okay, this is butane. Post ionization energy is quite smaller, yes, much smaller than this electron energy. Okay, this one, they are all around 10 electron volts. Okay, even benzene, okay, post ionization energy is only 9.2 electron volts. Okay, that is a pi electron ionization energy. All right. Okay, let's compare electron ionization, and another way is which is chemical ionization. Okay, uh, for this very is a special looking molecule. What's the name? Pentobarbital. Okay, this one. When you use electron ionization, this molecular nominal mass is 226, but there's no peak. 226 peak. Can you find it here? Maybe not. All right. Maybe here, very small peak. That means with electron ionization, uh, molecules are fragmented into many small species. Okay, but there are very two big peak. Okay, but when you employ the chemical ionization method, and then here is a molecule like a peak, right, at nominal mass of 227. Okay, but this peak is very strong, but not the strongest one. Okay, strongest one is found here at 57 nominal mass. Okay, but uh, but uh, these two spectrum shows that chemical ionization, preserve, molecular peak. But why here proton is added here? You will see soon. Okay, you will see soon. So with electron ionization, uh, there are there is more fragmentation. Usually, you cannot see molecular peak, but with chemical ionization, you see the molecular peak here. Okay, although a proton is added. Okay? But fragmentation may be good because fragmentation pattern. Okay, there are many fragmentation patterns gives an idea of a molecular structure. Okay, with chemical ionization, it is easy to know the molecular mass, but it is very difficult to the uh, infer this molecular structure. But with this examining the fragmentation pattern from electron ionization, you may infer, okay, this molecular structure if you are well trained. Okay, and the base peak. What is base peak? Base peak is the most intense peak here in this case. Mass number 141. This one is base peak. Okay, and in this case it is mass number 157. This is the base peak, and uh, uh, base peak is assigned 100%. Okay, this is the usual representation of a mass spectrum. Okay, so you pick up the base peak and then assigned 100%, and other peaks are you know uh, displayed relative to this base peak. Okay, the peak intensities are relative to the base peak. Um, but electrons with 70 electron volts are most commonly used for the electron ionization. Okay, this is common electron energy. Yeah. So with this high energy of electrons, uh, so it produces exclusively cationic molecular products. Okay, as I said, either cations or anions are produced, but with this high electron energy, you know, cationic molecular products or fragmentation products are exclusively produced. But if you employ lower electron energy, you may produce negative ions. Okay, by these two mechanisms. Okay, so resonance capture. Okay, this one. Mm, this electron energy is quite low, and then now this molecule simply capture. Okay, electrons, and then this is a molecular anion, not cation. All right, and also maybe dissociative capture may take place. Okay, now this one, XY, this is one molecule. Okay, um, and it accepts electrons, and then this molecule is dissociated. Okay, and one fragment takes a negatively charged ion. Okay, but I don't think this is a good way, right? Now let's consider chemical ionization. As the name indicates, you use chemicals to ionize your molecule. Okay, it produces less fragmentation than electron ionization. For chemical ionization, the ionization source is filled with a reagent gas such as methane, isobutane, or ammonia at a pressure of 100 Pascal. You see, 100 Pascal is about 1 millibar or 1 torr. All right. Yeah, here is the principle. This one, if we use methane as a reagent for chemical ionization, and now it is ionized by electrons. Okay, so now you produce this one methane cation radical. Okay, and methane cation radical reacts with another methane, and this one CH5 plus cation, this cation is produced, or this methane cationic radical now lose the hydrogen radical. It becomes CH3, the positively charged ion, and this one reacts with methane and it forms this one C2H5 positive the ion. Okay. Anyway, here this one this species and this species are a potent proton donor. Okay. Let's consider only this one. Okay, CH5 plus. This one is potent proton donor that reacts with analyte to give the protonated molecule MH plus. Okay, now this one uh, what collide with your molecule of interest, and then the proton here, okay, transport to this molecule. So this molecule M becomes a cation, but protonated cation MH plus. Since proton is added, so you see here, uh, you know, mass number, molecular mass plus one. Okay, this mass peak. Okay, that's why you see, mass number one added this molecular peak. Okay, protonated molecular peak. Right. Ammonia or isobutane are used in place of methane. Okay, to reduce the fragmentation. If you use bigger molecules like isobutane or ammonia, and then the fragmentation is reduced. Okay, these regions bind the protons more strongly than this thus methane does, and impart less energy to this protonated molecule when the protons is transported to this molecule. Okay, but still a negative ion can be formed. This is molecule, and then if it collides with chloride, and then it forms this anion. Okay, this is anion, negatively charged ion, or this molecule now react with hydroxide ion, and this one is formed. Okay, what is the resolving power of a mass spectrometer? Resolving power. There are two definitions for resolving power. One is you divide mass by mass difference you know between these closely spaced peak. Okay, here look at that. If you use this definition, and then there are two peaks here. Okay, and let's see, this mass difference is only one. Okay, one is at 500 and one is 501. Okay, and then what's the m? M is, let's see, this is 500. Okay, let's take this one, and then resolving power is 500. Okay, or there is another definition for resolving power: m divided by m 1/2. What is 1/2? Okay, 1/2 is the uh, mass difference at half maximum. Okay, in this case, at half maximum, this width, that's mass is 0.481. Okay, and if we use this definition, the resolving power becomes more than 1000. Okay, yeah, but either way is okay. Yeah, either way, but you have to define, yeah, which resolving power equation you used. Okay, in this case, this is not well defined. Okay, very poorly resolved. Yeah, this mass spectrometer is bad one, and uh, m here is 500, and what is the m 1/2? Now you deconvolute, yeah, this peak into two, one and two, and here this m 1/2 is one. Okay, so if we use this definition, you have a resolving power of 500. Okay, wow, this 500 and this one is the same. but this is a poorly defined, and this is a well-defined peaks. Okay, the difference is because of you use different resolving power. Okay, yeah, but actually, this resolution is really poor. Okay, and if you use a high resolving power mass spectrometer, you can differentiate very small difference. Okay, okay, here is an example. Yeah, using 208 lead. Yes, the mass number is 208. Peak in figure here, the first figure. You remember this one. Okay, find the resolving power from the expression of m over m1 half. Okay, and uh, half height from the figure. You can see the 0.146. Okay, okay, let's see again this one. Now we are considering this one. Okay, mass number 208. Yeah, this is a half. The mass one half is 0.146. Okay, and then this mass number is 208. Okay, so the resolving power is uh, 1.42 times 10 to 3. Okay, this is good actually. Okay? So an instrument with a resolving power of this number separates peaks where near mass to charge ratio of 200, but gives a barely discernible separation at mass number. If a mass number is 1004 uh, to 0, right? With this reserve power is not enough. Yeah? If this mass to charge ratio uh, is this one. Okay.